Welcome to the molecular orbital model. So let's re-examine the resonance that we saw in the Lewis structure for nitrate. Right? So here we see the Lewis structure for nitrate. I've left out here the lone pairs on the oxygens. I'm assuming at this point that you can draw them in yourself. So the Lewis structure shows two nitrogen-oxygen single bonds and one nitrogen-oxygen double bond. And where that double bond is can vary depending on which resonance structure that we see. So because the double bonds are stronger than the single bonds, we should see two different nitrogen-oxygen bond lengths for nitrate. But we only observe one bond length for nitrate, which means that something is wrong with our localized electron bonding model or our hybridized electron bonding model, because neither one of those can adequately explain why we only see one bond length there. So resonance implies a sharing of a double bond amongst all the atoms that could be doubly bonded, which means that we really have each nitrogen-oxygen bond really is acting not like a single bond or a double bond, but it's somewhere in between. It's a 4/3 bond, right? So really what we see is one structure that looks something like this, where each of the solid lines represents a single bond, and each of the dashed lines represents 1/3 of a bond. Right? In this way, we have a 4/3 bond between each oxygen and the nitrogen. And now we have one bond length. That bond length is shorter than a single bond, but longer than a double bond between nitrogen and oxygen. So the localized electron bonding model can't account for this observation because it's assuming that the electrons are localized. In order for the resonance structure to be happening, those electrons have to be able to move around the whole molecule, not just between the nitrogen and a single oxygen. It has to be able to go to all three of the oxygen atoms. So we need a new model that can account for this resonance. So the localized electron model also requires electrons to be paired, so it also can't explain any molecule that contains unpaired electrons, like in radicals. And so we turn now to the molecular orbital model. So let's look at a molecule of hydrogen gas. Right? So with hydrogen, we have two hydrogen atoms bonded together. We've got two electrons being shared in between. The formation of hydrogen from our separated hydrogen atoms looks something like this. It liberates 432 kilojoules per mole of energy, right? That's what that negative sign means, is that the energy change is negative, meaning the final products have less energy than our initial reactants do, so we're letting off energy, we're releasing energy from forming this bond, which should make sense because we're not breaking any bonds, we're forming bonds. Breaking bonds costs us energy, we have to put in energy. Forming bonds releases energy, we get energy out. So if the electrons in hydrogen are occupying atomic orbitals, as they do in the separated atoms, then the enthalpy change there should be zero. We shouldn't get out energy, because the atomic orbitals aren't changing in energy during the bond formation. So the fact that we observe a change in enthalpy means that we can't be using the atomic orbitals to form the bonds. We have to be using something new, something that is lower in energy, that allows those electrons to get lower in energy and release energy to the environment. So these electrons have to be occupying molecular orbitals, or MOs, which span the entire molecule, not just one of the two atoms. So molecular orbitals can hold two electrons, again with opposite spins, just like the atomic orbitals can. The shape of the molecular orbital indicates the probability that the electron is found in a region of space. Only now, it's no longer a region of space that's just centered around the atom. It's a region of space that's delocalized over the whole molecule, or potentially over the whole molecule at least. So we assume that the MOs can be constructed by combining the atomic orbitals together. So maybe with one of them, with MO1, we add together our 1s orbital from hydrogen A and our 1s orbital from hydrogen B, and in the other one we subtract them, let's say, so we have 1sa minus 1sb. So MO1 and MO2 are molecular orbital 1 and molecular orbital 2s. 1sa is the 1s orbital from atom A, and 1sb is the 1s orbital from atom B. So here's a sort of a picture of showing what's going on. If we add our two orbitals together, we have a positive sign there, a positive sign here, which means that overall we get a bonding orbital, we get an orbital that looks something like this for our molecular orbital. Now, our nuclei here, our nucleus for this B atom is in the center there, the nucleus for the A atom is in the center there. We're not moving the nuclei, so if I'm drawing them the same distance apart, it's something like here and there. I think that's about right. It's about the same distance as over there. So now what we see here is that there's a lot of electron density in between the two nuclei. So this nucleus sees a whole bunch of electron density on the right side, whereas before it was spherically symmetric around the nucleus. So here, this nucleus is going to tend to be attracted that way. This nucleus is going to tend to be attracted to the left. So they're both going to be pulled inwards for that bond. On the other hand, if we have a case like this, where we have this one minus that one, it doesn't really matter which one is positive and which one's negative, because they're symmetric. So now we get an antibonding orbital. So here, now we have our nucleus sort of there, and here, something like that. Only now, this nucleus sees a whole bunch of electron density on the outside. So it's going to tend to be pulled outwards. And this nucleus sees the same thing. It sees electron density on the outside, and it sees another proton in here that's repelling it. So this orbital, MO2, molecular orbital 2, is an antibonding orbital. If you put electrons in there, you'll tend to move the nuclei farther apart. But this one, MO1, is a bonding molecular orbital. If you put electrons in that one, you'll tend to pull those nuclei together and form a bond. So the shape and energies of the molecular orbitals for hydrogen are shown here. So we started out with two 1s orbitals, one from atom A, one from atom B. They each had one electron in them to start with. Here they're shown with the electrons both spin up. Doesn't really matter. Just by convention, we write the first electron in an orbital spin up. So here, now you can see that this MO1, those electrons are going to want to be in that orbital. It's going to be a lower energy orbital, because now an electron that's in this part of the orbital can now be attracted by two nuclei, by two protons instead of just one, as it was in either of the atomic orbitals. And so that's going to be an orbital that's lower in energy. So we can move this electron down and lower its energy. We can move that electron down and lower its energy. One of them we have to flip to the opposite spin. But then the other molecular orbital has to move up by exactly the same distance that this one moves down, because the average between those two has to be the same as the average between the two atomic orbitals. So this molecular orbital, MO2, has to be less energetically favorable. That has to be pulling our two atoms apart. And so it would be less energetically favorable to put this electron up there. We would have to put in energy to get that to happen. But we know that that orbital is not occupied in our molecule because, in fact, we get energy out. We get energy out in forming our molecule, so that means that the bottom one, MO1, the bonding orbital, has to be the one that's occupied. So MO1 has electron density between the two nuclei, the black dots in the diagram on the last slide, and thus causes the nuclei to experience an attractive force towards the electron density between them if the orbital is occupied by electrons. If it's not occupied by electrons, then it doesn't matter. We call this type of molecular orbital a bonding orbital because it contributes to bonding those two atoms together. MO2 has a node between the two nuclei, that empty space between them, and with diminished electron density between our two nuclei and a greater electron density outside the two nuclei, and thus our two nuclei don't experience an attractive force, but instead they experience a repulsive force if the orbital is occupied by electrons. If it's not occupied by electrons, then it doesn't matter. Again, we call this type of molecular orbital an antibonding orbital because it tends to push our molecule apart, pushes our atoms farther apart. It sort of anti-bonds them, it makes them move apart. So MO1 is at a lower energy than MO2, so we're going to fill that orbital first. The MO1 will be occupied by electrons before MO2 is. Furthermore, MO1 is at a lower energy than the atomic orbitals, which means the hydrogen molecule is more stable than the separated hydrogen atoms. So we've successfully explained why hydrogen will bond. So note that because the electron density for both molecular orbitals is centered along the line connecting the two nuclei, both of these molecular orbitals are sigma molecular orbitals, not pi molecular orbitals. Also note that once the molecule is formed, the molecular orbitals are formed and the atomic orbitals no longer exist. We're using up those atomic orbitals to form the two molecular orbitals. Those two atomic orbitals are destroyed. They're mixed together to form something else. So this is something like hybridization, only now not hybridization within one atom. It's hybridization over multiple atoms within the molecule, combining together multiple orbitals to form the molecular orbital. So the atomic orbitals no longer exist because the atoms have become, because the hydrogen atoms have become a new entity. They now are a hydrogen molecule, not just two hydrogen atoms separated. So we can assign symbols to each of these molecular orbitals. MO1 we can call sigma 1s, and MO2 we can call sigma 1s star, where this star, this asterisk, indicates an antibonding orbital. So we can now write molecular electron configurations, just like we could write the atomic electron configurations. So the hydrogen molecular electron configuration is sigma 1s2, indicating that we have two electrons in the sigma 1s bonding orbital. So note that the number of orbitals is conserved. We started out with two atomic orbitals, this one here and this one here. We ended up with two molecular orbitals. The number of electrons is conserved, the number of orbitals is conserved. Furthermore, the average energy of the atomic orbitals is the same as the average energy of the molecular orbitals that they combine together to form. So now let's look at the H2 minus ion. So if we put in one extra electron. So this ion now has 3 electrons. We couldn't describe this before with the localized electron bonding model or with the hybridized electron bonding model because they had to be working with electron pairs. Now we can work with an extra electron, an odd number of electrons. So 2 of the electrons are placed into our sigma 1s bonding orbital, and one of them has to be placed in the remaining orbital. Now remember, these 2 orbitals go away. They get mixed together, so we don't have them available. So now we have the sigma 1s. Well, we put 2 electrons in there. We need to put 1 more electron in. That has to go into the sigma 1s star, the antibonding orbital. And this means that when we increase that energy, that sort of negates the lowering in energy of one of the other electrons. And so now this will be less energetically favorable than the hydrogen molecule was, but still more energetically favorable than separated hydrogen atoms. So the increased energy of our electron in our antibonding orbital effectively balances the decreased energy of one of the 2 electrons, so it's half as stable. And we want some way of measuring this stability. How stable is it? Right? So we want to be able to talk about something like bond order. So to indicate the strength of a bond, we use the concept of bond order. How strong is that bond? Is it a single bond, double bond, triple bond, and so on? So the bond order is equal to the number of bonding electrons minus the number of antibonding electrons divided by 2, because each bond is composed of 2 electrons. So now we're able to talk about something like the bond order for the hydrogen molecule. We have 2 bonding electrons because they're both in the sigma 1s orbital, minus 0. We don't have any antibonding electrons because we only have 2 in the hydrogen molecule. Remember, this one is not charged. Divided by 2, so 2 divided by 2 is 0. 2 minus 0 is 2, divided by 2 is 1. So the bond order for the hydrogen molecule is 1. That's what we expected. We expected to see a single bond in hydrogen. But if we have the H2 minus ion, well, there we have 2 bonding electrons, 1 antibonding electron, divided by 2. So that gives us 1/2. So now we're able to talk about, well, we only have half a bond. Now, by putting that extra electron in there, we've weakened that bond by 1/2. And what this means is that now that molecule, that ion, should be significantly easier to break apart. And now we can talk about the strength of bonds that aren't even necessarily single, double, or triple bond. They can be half bonds, 1.5, 2.5, and so on. We can't get past 3 still. But a larger bond order now indicates a stronger bond, so a more energetically favorable state. It no longer has to be an integer value. It could be a half integer as well. So a larger bond order indicates a stronger bond than a smaller bond order, which is a weaker bond or a less energetically favorable state we're getting less energy out by forming that from the separated atoms. So now let's look at a diatomic helium molecule, He2. So each helium atom has an electron configuration of 1s2 before bonding. So we have something that looks like this. So 2 of the electrons get lowered in energy, 2 of the electrons get raised in energy. The lowering and raising is equal in magnitude, which means overall there's no net energy change, which means overall there's no driving force for this bonding to occur. If we look at the bond order, we have 2 bonding electrons minus 2 antibonding electrons. That's 0 divided by 2 is still 0. So that means that the bond order is 0, which means there's no bond in between. So this means that our helium-2 diatomic molecule is not stable, which agrees with the observation that helium exists as individual atoms, not as diatomic molecules. So that was the molecular orbital model.